We've got a lot of challenges in hardware design. Today and few days before, you get here on EMC Europe conference. So I think you know something about EMC, yes? Probably you don't know me, yes? Because you are not from Poland. In Poland, some guys knows me, like Tomasz, because I teach EMC in Poland. I'm kind of EMC teacher, full time. So I've got own consulting and training company, small company. We are making trainings, workshops, and consulting for EMC issues, usually in Poland, but also around and international. So I worked on University of Technology in Wrocław, so the main organizer of this conference. I worked there in EMC laboratory with Artur, Zbigniew Juskiewicz. From 2016, I teach EMC, mostly hardware designers, because electronics hardware designers do their job very good, because what they need to do. Reason.
Projecting. We have a
project.
Qualified from making what's
Okay, but on the beginning, we've got some schematic, so some concept. We've got some concept. Okay, this device should do this kind of interfaces. Okay, then we've got block diagram and schematic. On this stage, also, we need to consider some EMC problems, yes? So, what we do during schematic time?
Predict disturbances.
Predict disturbances, okay, and then what?
Apply some filters.
Place some filters. Filters, what kind of components are in the filters?
Choke filters.
Chokes, okay, so we've got chokes. Chokes means inductor. And second, yeah, we've got only two components in EMC. No, mostly. Chokes, like inductors, and capacitors, okay? Okay, ferrites, I think like chokes, inductors, yeah, but ferrites, chokes, inductors are in here, capacitors, and also for ESD, TVS, varistors, and so on. But okay, so we've got two kind of components we placed on schematic. Someone experienced came to our project, looked on schematic, looks okay. We've got EUT, equipment under test. Okay, we've got some connectors, microcontrollers. So we've got the coupling, we've got some filtering in places that may cause problems. Okay, so we've got everything on the schematic. What can go wrong? And we make layout. And that's the problem. Because on the schematic, we usually see something like this, or this.
Ground. Local ground.
It's connected to ground, to local ground. If we place the digital analog, but it's connected to the ground. And on the schematic, we can have big picture, big schematic, and this trace and this trace, we've got the same marks. Okay, so it's connected to the same ground on a schematic. But then, we are looking on our layout, it's not the same point. Is the same or not? Looking on schematic is the same. It doesn't matter where I'll place capacitor. But in the real world, you know exactly that it has huge impact where I placed my components, how I prepare my PCB, we've got not a lot of rules. We've got only few rules how to design electronics for EMC. Do you agree? Or there's a lot of rules? There are some rules. Only some rules I would show you my point of view, but sometimes one rule and another we can't do simultaneously good from this side and this side. Also, sometimes we've got this consideration make good EMC, but someone came us, what about electrical safety? You can't connect PE on your enclosure because we are in class electrical safety. So, yeah, I'm also mountaineer, diver, and so on. So, different chambers, different laboratories around Poland. So, during development stage, we've got hardware design, software design, tests on our desk, everything works. Then we get software, integration, and of course, nothing work good. We are waiting for software, waiting. Okay, now it's good. Testing and evaluation. Okay, we've got problem. And that's why EMC, for normal people, not on this conference, is, they've got some standards, but it's something strange, they call it black magic, and so on. It's not so important. Important in this business is money, cheap components, make it faster. But why EMC is so important? Because project is going, then evaluation, and stops what? Everything. Because it's not so simple to go, oh, I go here or here. Sometimes we need to go here. And what's there? There, manufacturing, production is waiting for us. Of course, we've got different, but they are waiting. So, huge plant is waiting for us to make design. How many dollars are wasted because they're waiting for us? A lot. So, EMC is very important because without EMC, without testing, evaluation, without compliance, we can't send project for production. When we look on our PCBs, so this part is simple, this part is simple, this trace is simple, everything is simple, but we need those, every piece, every simple piece, connect in one place, and that's why we've got so complex problems. Because, of course, we would like to make in our watch everything, measure our heart rate, Bluetooth, Wi-Fi, and so on. So, integration, smaller things, complexity, a lot of traces, this coupling to this. Time to market. Of course, we need to do our designs much faster. Time to market is very short, because in 2 years, my medical device will be useless, because new technology is coming and so on. What application notes? It's waste of time. Do your design, because we need to show our management, our directors, that we've got milestone. Here is time for evaluation. Why you are looking for those stretch things on the beginning? So we are looking maybe to simulate something. Maybe we don't need to go to laboratory. We can simulate something. And of course, it's very good. We've seen a lot of presentation during this conference about modeling, about simulations. You probably know that simulation is as good as our model. So, to prepare good model of our real device, real PCB, it's huge work to do. If we've got millions of units. Okay, probably we could spend time, money, some people to prepare simulations for all device. Business case, we can't spend a lot of time, money for software to do simulation for every our small equipment, especially if we've got not a lot of units in production. So we try to simulate parts of it, only considering the main problems, like which trace is important. It could be sensitive, yeah? Sensitive parts, sensitive traces. So we've got small analog signals. We need to amplify them. So if we've got any disturbances in it, it can destroy. So we are looking on which trace, which path, which component could be sensitive. Because EMC, we've got two aspects, immunity and emissions. Yeah? And second, which path can emit something. Make emission. Like, what can make emission, big emissions?
Something switching.
Something switching, yeah? There is no problem about EMC. It's everything quite smooth, everything good. But then we're trying to switch off. Then switch on. And of course, EMC is in that parts. Physical phenomenons, physical field, electromagnetic fields, phenomenons in big picture, like chambers and system, but the same physical phenomenons, but in different scale, we can see on our PCB level in our components. So I'm trying to show you very simple experiments to show some rules and explain why they are important in PCB design. In EMC, we are learning something like that. To prepare for war with enemies, so with EMI, electromagnetic interference, we need to know our battlefield. Yeah? So, what's the map? What's the physics behind? What kind of standards? What kind of disturbances we can find in our environment? Because we've got different environments. Yeah? Then, what hardware design engineer should to know? How they will attack. Whoa. How they will attack us in a laboratory. So, what kind of weapon they've got? They've got ESD guns, burst, surge, RF signals, and so on. So, hardware design engineers should know something about laboratory, how they will test my equipment to prepare. Then, we are looking how to target our enemies, targeting spies. So we are looking for troubleshooting methods, simplified, not exactly like full compliant in a laboratory. So near field probes, yes, maybe simple antennas, current probes we are using. Then we can design our fortification, our castle to make protection. So it's our PCB. We are doing filtering, like bridges. We've got shielding, like walls around, and so on. So we look in this way. So prepare system for your EMI. We've got, of course, EMCs, electromagnetic compatibility. We can't destroy other systems, and also we need to be immune for disturbances in our environment. But also we've got kind of integrity, internal signal integrity. So when I send signal from here to here, receiver will receive the same what I sent in specific time and so on. So we have signal integrity and connected with those two power integrity, power delivery network. And the question is, where the current flows? How the HF, high frequency current, flows? Because sometimes we, as a hardware designers, we design something like architectures. They prepare some very good path. This is good path. Go there. But people sometimes goes other way. Okay. Why? Because architecture doesn't know human nature. And also we need to know what's the nature of high frequency current. Because in a primary school they teach us something like that. The current flows in a path or the lowest resistance. In a preliminary school. Now, they told us that current flows in the lowest resistance. Low resistance. And it's kind of true. Resistance, especially for DC current. But when we go into AC current, okay, so we are getting, one more thing. We are getting something more than only resistive part. A few seconds we will speak about. Then, when we design some radio equipment, we know exactly, like, for example, kind of radio telephones, we know exactly what kind of frequency we work. For example, 400 something like megahertz. We know exactly which frequency we need to consider when I'm preparing my path from transmitter to antenna. Yeah? We know it exactly. But when we've got digital signals, what kind of frequency we need to consider? We need to consider full spectrum of our signal. And this is our spectrum in frequency range. And this is literature example. We've got 1 megahertz square wave and 0.1 nanosecond rise time. Here is our operating frequency, 1 megahertz. So how far the spectrum goes when we've got 0.9 nanoseconds? How far? From 1 mega to gigahertz. Here we've got 2 gigahertz. Yeah? So we've got this kind of spectrum for our signal. So we rise our signal. So we need to make it very sharp. We need to make good resolution for this. If we need good resolution, we've got high frequency content. Yeah? It's okay or not? It's understandable? Or so obvious? It's so obvious, okay? That's why we've got problems, because the impedance the impedance is, of course, resistance, but we've got inductance and capacitance. And it's also connected with frequency. So, when I've got my digital signal, my impedance of the trace or the path could change. That's why, of course, usually I prepared this kind of workshop for 2 days, so I'm trying to make it very short. But of course, here we've got kind of theoretical concept, but also practical. We can measure it, but in two ways. In near field probes, using near field probes, and in a chamber. So this is the same simple PCB. I measured in using near field probe, and then I place in chamber. What we can see here is a little bit higher, lower, higher, lower, but the spectrum was kind of this, going down. So it should look like here, like this. Why in chamber we can't see the same spectrum?
Because of different environment,
not really the problem. Why? In a far field, we've got different results than in a near field.
Frequency range. Different frequency range.
Oh, frequency range is kind of the same here and here.
Some reflections.
Maybe reflections. What else?
General geometry, connected cables.
Yeah, because we've got kind of source. Then we've got trace, and we've got antenna. And here our source is this kind. This is our source. But then we need to look on our, of course, attenuation of transmission line, but also we should look on our antenna characteristics. Because, like, we've got this kind of antenna, it's log period antenna, logarithmic periodic. It has something like this spectrum. So here emit a lot, here not.